Welcome to the next video in mathematical statistics. This is video 2 where we introduce probability. It corresponds to part 1, chapter 1, section 3 of the textbook. So keep in mind where we just came from. We were talking about events, but we didn't mention probabilities at all. So what you want to kind of imagine is that there is sort of a space of events over here, and maybe what I really should say is that this is my sample space omega, and then my events will be some subset, right? So E will be some subset of omega, and you could have like an E2 that might intersect it, and maybe you'll have an E3, right? Just all kinds of various possible subsets of our omega, our sample space. So these are our events. And then there's going to be the probabilities. Probabilities are going to be on a number line always from 0 to 1. So these are the probabilities of the events, right? And so we have this function p that associates each event with some particular probability. But the important point is just to emphasize that we have the events on the one hand and probabilities on the other hand. And in order to call these probabilities, they have to satisfy certain properties. Now, for one thing, they have to be real numbers in the interval from 0 to 1. 0 will represent an impossible event. So if you want an example, think about like tossing a coin and getting both heads and tails showing at the same time. Well, that's impossible, and so we call that probability 0. Again, within the context and logic of a normal coin toss, then we could also have things that have probability 1. These would be certainly true events, like getting either a heads or a tails showing on a coin toss. And some people will say like, oh, couldn't it land on its edge or whatever, but come on, give me a break, right? We're in the context and logic of a regular coin toss. If it helps, you can read these things as percentages. So 0 can be thought of as 0%, and 1 is the same thing as 100%. We won't often deal with percentages, but just if it helps to imagine things that way, you're free to. But here's the formal definition of a probability. And what we're really going to say is anything that meets these conditions is going to be called a probability distribution. So what it has to be is for each event, right? If you take any event, which is a subset out of our sample space, the associated value has to be non-negative, right? We will not try to make any sense of the notion of negative probabilities in this class anyway. And the probability of the entire sample space must be equal to 1. So again, that's kind of like having heads or tails, and that has probability 1. Or if you want another example, if you had a die roll and you talk about getting the probability of 1 or 2 or 3 or 4 or 5 or 6, that's going to have probability 1. That's the probability of the entire sample space. So the probability of the entire sample space must always be equal to 1. And here's for sort of the most difficult of the axioms that we're going to have for a probability distribution. Let's explain this by actually starting from a more, sort of basic thing. Let's just talk about two sets, right? This is for an infinite family of events. Let's just talk about two for the time being. So suppose that A and B are some two disjoint events, right? So this is going to be an essential part of what we're talking about here, is that the two events must be disjoint. When they are disjoint, then we can say that the probability of their union, right? That's what this is all about, is the probability of their union. That probability is the probability of their sum. Now, what's important to recognize here is how the disjointness is an essential part of this. Well, first of all, let's just think about the probability of getting either a 1 or, and by the way, I'm going to write it with a disjoint union symbol. So I'm going to talk about the probability of a 1 or a 2 on a die roll. Now, why am I writing my union symbol as a square union symbol? And maybe I actually ought to do it over here to be consistent, because we're talking about a disjoint union. So the square union symbol means exactly the same thing as the regular union symbol. They're not different in what they mean. When I write, the set 1 square union, the set 2, I'm just talking about the set of 1, 2, right? So this really is just the same thing as the normal union. But I just write it as a square when the two sets are disjoint. And the reason for that is that, this axiom comes up so often, and you really have to have disjointness to use it. So it's always nice just to have a visual marker of when the two, when you're unioning two disjoint sets, because it is a marker that the following move is valid, that we can turn it into the probability of 1 plus the probability of 2. Now, let's check each of these with some amount of intuition. So if we were to just talk about the probability of getting a 1 or a 2 on a die roll, I think we know that that's a 2 out of 6 probability. If we talk about this probability, I think we know it's a 1 out of 6 plus a 1 out of 6. And all of this checks out, right? All of these things are equal to each other, so it all works out. It's nice and consistent. Now contrast that with what happens if you don't have disjoint sets, right? So imagine that we were to compute the probability of 1, 2, not disjoint union, with 2, 3, because they share the number 2. Now, this is the same thing as the probability of 1, 2, 3, right? Because the union of 1, 2 and 2, 3 is 1, 2, 3. That's an event with 3 elements, so that's a 3 out of 6 probability. Again, I'm just assuming that you've seen sort of like these uniform probability distributions, that you know how to do basic reasoning with probabilities of a die roll and so on. So that's this is all just an example for demonstration purposes, and I assume that much is familiar. So now contrast that with what you would get if you tried to use the sum formula and compute that as the probability of 1, 2 plus the probability of 2, 3, which in each case I think we know is 2, 6 plus 2, 6, which is 4 sixths. And it's not the same answer. They're not equal. So we cannot, right? So when the sets are not disjoint, we cannot use the sum rule, is what you might call this rule. So there you have it. That's this axiom 3 applied to two sets. Here, the general version of the axiom is applied to infinitely many sets, right? Any infinite family, you can take their infinite union, and if you take the probability of an infinite disjoint union, then you get this infinite sum of their individual probabilities. So that's axiom 3. Now, from these axioms, we can prove a first theorem. This will be very useful. It tells us that we can still compute the probability of the union even when they're not disjoint. We just get a slightly more complicated formula. So the probability of any two sets, whether they are disjoint or not, is given by the probability of the first set plus the probability of the second set, but then minus the probability of their intersection. So let's prove this theorem. So we're going to start from the probability of the union of these two possibly not disjoint sets. And as we think about what move might we make, you can kind of just survey the axioms available and think, well, given what we have here, there's not a lot to work with, and we have to be doing something with a union, it sure seems like. So let's try to think about how we could leverage axiom 3, right? The one that seems most relevant to a union. It applies only to a disjoint union, so we can't use it directly. But if you think about the set A union B and think about how we might try to somehow rearrange things so that axiom 3 can be used, well, we want to take A union B, I guess I should highlight it like this. This is A union B, and maybe try to decompose it into disjoint components so that so that axiom 3 could be used. And if you think about like what disjoint components could we break this into, well, somewhat arbitrarily, we could simply select A, and so far that does not overlap anything else trivially because all I've done is select A. But then if you think about what do I have left over that I still need to include to have A union B, well, it would be this portion of B, which is denoted B minus A, right? It is the part of B that does not intersect A. And notice that, A and this set, they are disjoint components, and when you take their union, you get the same thing as A union B. So we can in fact say that A union B is the same thing as A union B minus A, and these are two disjoint components, and that allows us to use axiom 3. So what we're going to start off doing is simply replace A union B with what we just showed is equivalent to A union B, which is this A disjoint union B minus A. And on that, we can apply axiom 3 to break up, right? In a sense, it kind of seems like a distribution. Maybe it's not the normal kind of distribution where it's just like multiplying a number into a sum, but it sure looks a lot like a distribution, so it could be helpful to think of it that way. And so we get the probability of A plus the probability of B minus A. From here, some of this looks good. We've got the probability of A. We know that is in the formula that we're trying to prove, but we don't have the probability of B. But we have part of B, right? This is B minus A. So we have part of B, but we would like to give it the part that it's missing, which is, in fact, the intersection A intersect B, right? If we could give it A intersect B, then we would be moving towards getting the probability of B. Now, that means I want to add the probability of A intersect B, but you can't just do that, right? Because if you just simply add it in, you no longer have an equal quantity, but you can sort of compensate, you can balance this out by then subtracting it back out, right? So we add it in and then we subtract it out. That means that we have a true equality. Now, if this is your first time seeing a trick like this, and this is a move that mathematicians make often, is to if there's something that I want in my expression, then I can add it in and subtract it out, or sometimes it's multiply it in and divide it out, but this is a fairly common trick. And if it's your first time seeing it, you might think, well, this can't possibly be useful, because if I add it in and subtract it out, then those two things cancel, and I'm right back to where I started. And that's totally valid. But I'm not going to do that, right? I know it's hard to resist the urge to cancel these two out. But the point of making this move is so that I can group these two things together, and after grouping them together, this thing will just kind of hang around. Which, by the way, is not a bad thing because we know that the formula we're trying to prove has a minus probability A intersect B anyway. So this is a good move. And what I'm going to do is I'm going to group these two terms together. And I'd like to turn this into the probability of B. Now, how do I justify that? Well, notice that B minus A and A intersect B, right, depicted here and then also here. These are two disjoint sets. And so I can use axiom 3 in reverse, right? So if the first use of axiom 3 looked like distribution, then here if I use it in reverse, which I'm free to do because they are disjoint sets, right? These two are disjoint sets, so I'm free to use axiom 3, and there's no reason I can't use it in reverse. And so it kind of looks like factoring the probability distribution out to the outside, replacing it in here with a disjoint union. But in any case, this is what we get justified by axiom 3, and then that just turns into the probability of B, and we're now done with the proof. Okay, let's see an example of using this. So let's imagine that we have a standard 52 card deck, and we would like to find the probability that I draw a random card, and it is either a heart or a king, right? So let's write this as the probability of H union K, right? So that would, H is like the event of a heart. It's got, 13 outcomes in it. K is the event of drawing a king, and that has 4 cards in it. But we're looking for the union. And so if we use the theorem that we just proved, we would have that this is an equivalent expression for that probability. And we know the probability of H, so that probability of H, that's, let's say 13 out of 52, why not? We could also say 1 out of 4, they're the same thing, but we'll just write it as 13 out of 52. King is 4 out of 52. It's nice to have everything out of 52 just because you can add fractions more easily when everything's all just automatically out of 52. And then minus the intersection. Now let's talk about that intersection. How many cards are there that are both a heart and a king? Well, there's just one, right? There's just one king of hearts. So we're going to subtract 1 out of 52. And when we simplify that, that's 17 minus 1 is 16. So 16 out of 52, which we could then simplify. I think, right, you could divide by 4 or, cancel a factor of 4 or something like that. But whatever, once it gets down to calculating numbers, I lose interest in the problem, right? The most interesting part is knowing how to analyze the problem. Now, one thing I want to just briefly reflect on is that what you can kind of see from our example here is that the formula we derived, right, this formula for the union, is effectively, especially if you already know the probability of H and you already know the probability of K, then effectively what you're doing is you're exchanging a probability of a union for the probability of an intersection. And is that useful? Why would you want, if you can count one, can't you count the other? Well, sometimes, and I think this is one of those times, it's just easier, right? It just is easier to find the probability of an intersection than it is to find the probability of a union. So, a lot of times it's just easier, so you'd like to exchange your union for the intersection. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.